This is about the machine learning strategy for deep learning. This is about the practical aspects that we have to consider when we are going up with machine learning projects that are related to deep learning. And when you are managing a machine learning project, or especially a deep learning project, with you have a set of data and you have a set of people who are working on different aspects of the uh, models, and you have to deliver some outcomes within a certain period of times, and you have to achieve certain levels of benchmarks or certain levels of accuracy or certain thresholds of uh, performance within the project, and how we are going to achieve each of these project outcomes within the given resources within the minimum amount of time possible. uh, that is the problem that we are going to uh, address in this lesson. This is somewhat uh, focused towards the management aspects, but not anything related to management, but how to manage a project to go to the success without trying everything that is possible, right? Because when you are learning these algorithms and the ways how to tune your deep learning algorithms, you learn a lot of hyperparameters, a lot of ways the data can be processed, how to engineer the features, how to tune the deep learning models, and what are the other machine learning models that you can use. And there are different things that you learn. But when it comes to a real world problem, you can't apply all these available options into your problem and see whether they are working, because that is not practically possible, because you have only a limited amount of time and you have only a limited amount of resources with you, so that you can try only the relevant options. That means you have to predict what are the things that you have to do first. That means what, when you follow which kind of approach, you will get better performance within a short period of time, which would help you to go to the long term goals of your project. And then you have to identify what are things that you have to do next. So that is what you have to be in your mind when you are managing a machine learning project, right? That is the strategy that you are going to practice during a machine learning project, right? So there are many ways that you can move ahead in your machine learning project, right? Say you have got a machine learning project and you have done something and you have created a model, and now you have a certain level of accuracy, precision, recall, and you can do something, but you have to improve more. What are you going to do? There are many ways of things that you can do, right, to improve your project. One is collecting more data, right? You can collect for more data. You can expend more resources and time to collect more data to get a better model. That is, of course, better, right? But that is expensive, right? Of course. And when you have a lot of data, you would need much more computational resources or much more time to learn the model, right? Although it may give better performance, and it takes a lot of time overall, right? So it may not be the always case when it comes to going ahead with the project, right? There are things that you can do within the scope of your project, right? And the other option is maybe you can get more generic data. Say you are, say, collecting the most uh, relevant data, or the for example, if you are collecting some images for your CCTV camera, if you are trying to collect the same camera to collect data, that would take a lot of time, and it would be practically, it would be, there would be certain difficulties, right? So instead of using the same CCTV camera, maybe you can get the images that are there, that are collected from other CCTV cameras. That means you can get generic data for training purposes instead of using the same most accurate or high quality data for training your model. Maybe you can get much more generic data to improve your model, right? Instead of using the exact data that is relevant to your project. Or the other case, in the other case, you can increase the training time. For example, if you have used a technique like early stopping to reduce the cost or the time for your model, and also as a form of regularization to avoid overfitting, maybe you can increase the training time to reduce the bias, right? Maybe you can increase the regularization using some other technique, using dropout or L2 regularization, and then you can avoid this early stopping uh, approach, and you can increase the training time, right? And as you have learned, there are different optimizers, not only the gradient descent optimizer or the commonly used Adam optimizer, but there are some other optimizers, right? And also even inside an optimizer, you can change the hyperparameters that are relevant to each of these optimizers, right? For example, if you have selected Adam optimizer, there are hyperparameters like not only the learning rate, but beta 1, beta 2, and so on. So maybe you can tune, actually, when it comes to in the practical world, the first thing, the highest important hyperparameter that you have to tune, if you hope to tune the hyperparameter, is the learning rate, right? Beta 1, beta 2 are less significant hyperparameters that you are going to train, right? That means once you have come up with some better results with learning rate tuning, then you can move on to beta 1 and beta 2 decay rates, right? Uh, so when it comes to different hyperparameters, there are different things, not different optimizers. There are different hyperparameters you would have to tune as well, right? And when it comes to a neural network, there are other things that you can tune. Not only the uh, optimizers, but you can change the number of neurons in each of the layer, the number of layers that you are learning, or and the regularization options like dropout. What is the dropout ratio of each of these uh, neural link, right? Neuronal layer, and also you can change the activation functions if you want, right? Uh, Maybe you have started with the ReLU activation function in the hidden layers and hidden layers, and maybe you can change that to some other uh, GALU or something like that, some different activation function, right? And there are different things that you can do, right? But you can't do all of them, right? And see which one is going to work. You have to identify what is the best thing that you are going to do at the moment with the current results, right? In the current status of your project, what are you going to do next? There should be only one thing that you have to do, right? Because you can't, the one option is that you can divide your team into several sub teams, and one team was for one sub team, you can ask them to change one thing and the other one to other thing and so on. But that's not practical, right? So you have to drive your team uh, for the same objective only by changing one thing, right? Only a single direction you have to follow. That is what we have to learn in this lesson. So in order to learn how we are going to change the direction of our project, let's take an example of an older version of televisions in your home, right? So maybe not in your current home, but if you think about your parents or grandparents' homes, you might have seen televisions like this, right? So there is a television. This is the screen. This is the cathode ray tube, right? This side it's a speaker, something like this, and this side you have a set of knobs, right? Set of knobs that you can use to tune the television, right? Something like that. Even inside, if you in the modern televisions, you won't see these tunes, not the modern televisions, but the CRT cathode ray tube televisions. But inside the cathode ray televisions, although these uh, knobs or the tunes are tuning knobs are not there, they may be located inside the TV itself, so that once you open the television in a workshop, they may in repair center they would have access to these knobs in this television, right? So what do each of these uh, television knobs do? So when it comes to this cathode ray tube, right? So this is a cathode ray tube where inside this cathode ray tube, it's like uh, there's a certain electron gun at the uh, other end or the back end of the TV, and from that from the cathode ray gun, it is emitting a set of electrons to the front screen, which is known as the phosphor, right? So once you hit the electrons to this particular screen, there would be some glow in this in that particular point. Then, and that is how the pixels related to the image are uh, scanned onto the television, right? And that is how the images are generated in this TV screen, right? So around this uh, electron cathode, right? So this is where the electrons are emitted. So around this, there are some certain electromagnets. That means a set of copper coils that are there, right? Set of coils. These are the two ends of the coils in different ways, and there are certain plates of electric fields that are there around this electron beam, right? So these supplies to these magnetic fields, and these plates are controlled the by these knobs, right? So what do they do? Say you want to tune the image projected on the screen. For example, say your image is not centered, right? So it is somewhere here, right? You want to move it here, right? So what you do? You should change the vertical position, right? So there's a certain knob for vertical position or vertical position tuning, and then you have to move this image to this side, right? So there's a horizontal image tuner, this side or this side, right? Then you can rotate this knob is corresponding to the horizontal alignment of the image, right? So these knobs will be are connected to each of these magnetic fields or the electrical fields, right? So they will be adjusted so that the image projection would be changed depending on the voltage or something given to each of these connections, right? So and then there's another thing where your image is not focused to the middle of the screen, so there would be another knob where you can focus to make the image larger or something, right? Or to smaller, or change the size of the focus of the image on the screen. And so on, there are different ways that you can do, right? So maybe you can tilt the image. I don't know that is possible in a TV, like the rotate the, whether you should rotate the image this side or that side. So these kinds of controls are not, may not be there in the television, but in the computers or computer screens, there may be certain image processing operations. Uh, Not only these are, those knobs are there in the computer, but in an ordinary computer, in an image processing system, the same kind of knobs would be there in something like a Photoshop or something, right? A tool like that, maybe, and you have some rotating and all those things that are there given in each of these knobs, right? So what I'm going to tell is that what we are going to learn is how to tune these knobs so that you can get the optimum image, the optimum projection on the screen, uh, while there are many knobs to be tuned in this television, right? Like horizontal movement, vertical movement, focus, rotation, so on. If you are trying to rotate all these knobs together, one knob in the one hand and the other knob in the other hand, it would not be an easy job to tune your image, right? So one is changing the vertical process and other one is trying to change the focus and so on. So that would not be easy, right? So you have to, so how are you going to tune this kind of TV when you have these kind of knobs into your control? You have to independently tune each one of them, right? One after the other, so that you tune one thing first and then go to the other operation. This one first, this two second, this two third, this two fourth, and so on, right? Horizontal uh, movement first, the vertical movement first, zooming first, focus third time, and the rotation in the fourth time, and so on. Right? So you are not going to rotate the knobs, all these knobs at the same time, right? You are focusing one at a time, right? And this process of independently controlling each of these knobs is known as orthogonalization, right? Which is similar to the options that we have in our machine learning project, right? So all these options that you can do in your machine learning project are acting on the results of the project, but if you are trying to change many of them at the same time, you it would be much more hard, which means much more difficult to go to the results that you want to achieve uh, if you do several of them at the same time, right? So when it comes to the options that you have in your hand, you have to follow the same orthogonalization principle to uh, adjust one variable at a time, keeping the other variables constant, right? So, and uh, in order to achieve this kind of scenario, right, it is not always possible, whatever the knobs that are available for you, right? So for this kind of scenarios where you have the vertical, horizontal, zoom, and rotation, you can do it one after the other. But because why? What is the reason that you can change one at a time within this set of variables? That is because these variables are orthogonal to each other. That is why it is known as orthogonalization. Orthogonal means one's effect is not uh, affecting the other options or the other variables affect, right? So the changes are orthogonal to each other. That means it is something like this. So you have two dimensions. Say this is the x dimension and this is the y dimension, right? So once you change the x dimension, it won't affect the value of the y variable, right? So when you change something in the y variable, it will not be affecting the x variable because x and y are in x and y are orthogonal to each other, right? So this is a 2D space. So if you have another dimension like z or something, right, where x and z are also orthogonal, y and z are also orthogonal to each other. In that case, you can change the z so that y and x are not getting affected, right? Or you can change x without affecting y and z because these dimensions are fully orthogonal to each other, right? In this kind of controls also, when you are changing the vertical position, because it is orthogonal to the horizontal position, you can independently tune vertical and horizontal positions orthogonal to each other, right? Similar, and this zooming also, it is somewhat different, right? So the horizontal position and vertical position are not connected to the zooming. So in the rotation, it is something else, right? So because these features are orthogonal to each other, you can use the orthogonalization to tune the television. Similarly, you have to identify the orthogonal variables in your machine learning project so that you can tune these variables independent from each other so that you can achieve the final objectives of your project. In your machine learning project, you may have several phases, right? The first phase would be reduce the training set cost, right? That is the objective of the first phase, right? Where when you have a training set, so what you do in the machine learning is first you train it with the training set, right? So at this phase, your objective is to reduce the training set cost, right? For reducing the training set cost, what are the optimizers that you can use or the variables that you can change? You can use a bigger neural network, right, for training better, or change optimizers like the Adam optimizer and so on. And you can use techniques like early stopping, right, to reduce after some time the test set error may arise, right? So maybe you can use early stopping to training set cost or something, right? Or actually it is not totally correct, but say that early stopping is something that you can use in the training phase, right? Let's assume like that. And then you move to then once you create a model, right, you test with your test set. But in that case, because you have multiple models to be trained, you are testing with the validation set or the dev set, right? So we are not going to the test set. You are testing at the later stage, right? So in order to test your trained model, you are going to use the dev set or the validation set, right? So in this phase, what your objective is to reduce the dev set cost, right? So in order to reduce the dev set cost, uh, what you are optimizing is about how you are going to optimize is using the regularization, right? So once you find that your uh, although it is working well for your training set, but working bad for having a higher error for dev set, you can use regularization, right? Or you can use a larger training set here, right? Different kinds of things that you can do, right? Or you can use early stopping to reduce the dev set error, right? when it comes to early stopping, right, both of the training and dev sets costs are getting affected with early stopping. Right? And let's move into the other phases of the machine learning project where you can, when you are testing again with the test set, right? So which is to get the test set error, right? Then you uh, can reduce the error in the test set by using a larger dev set, right? So if you are good using a larger dev set, you can reduce the test set cost, right? Because you don't have to use that test set for dev set purposes, but if you are using a larger dev set, you can get much more higher accurate numbers, right? And you can use the, so these are just examples, right? These are not exactly the correct uh, theories that we are going to do, right? So we are just trying to uh, go to a certain this, we are using this as a certain example for the orthogonalization, right? So that is why we are using this. These are not exactly correct, but we are going to derive something out of this concept, right? So once you test with the test set, what you're going to do is we are going to reduce the error in real world application, right? So once you change the dev set cost, change the dev set or cost, right? You can have better dev set to change it to a better dev set, and you can change the dev set cost, right? Or something like that, and then you can tune for optimize for the this phase, right? So when it comes to these features, large dev set is only affecting this phase. Dev set or cost is only affecting this phase. Regularization, large training set are only affecting this phase. These bigger neural network or different changing optimizers are affecting only this phase. But when it comes to early stopping, that is affecting both this phase and this phase, right? Because of that, this early stopping is affecting more than one phase. You can't consider early stopping as a orthogonal uh, optimizer, right? So we can't use early stopping for optimizing both this one and this one, these phases, right? So you should not use early stopping here. You can use the other optimizers for optimizing first one by one, right? First, you can change the bigger neural network for optimizing that at the training set time, and then you can change the regularization for uh, tuning for optimizing for the dev set cost, and then these things and these things and so on, right? So that is how you find the uh, optimizers or the which are orthogonal to each other, which are not affecting more than one phases, so that you can use those optimizers for optimizing the in the phase that you are there, right? Without affecting the other phases, right? If the other phases are getting affected, then it would not be easy to use these optimizers to tune, because once you change this one will get also get updated. In that case, you can't use it, right? Yeah. And when it comes to evaluation, right? So that is how we, so up to now what we have learned was how to use the uh, tuning knobs or the tuning parameters which we are going to use. We said we have understood that we should be using the parameters that are orthogonal from the other phases or the other uh, which are not affecting the other parameters or not affecting the other phases and so on, right? And when you are optimizing your project towards uh, to a certain goal, right? Uh, there may be several evaluation matrices for your machine learning project or the machine learning model, right? However, uh, when you are when you and your team is moving towards a certain goal, you can't optimize to all the evaluation matrices, right? You can only focus to single metric first at a time, right? So you have to optimize only to a single number at a time, right? That means you have to find an optimization phase to be optimized at the time. Maybe once you are good at that phase, you can move to another phase and optimize to that phase, right? But at the time, you have to only focus to a single number, right? Let's take an example, right? For example, a binary classifier may need to optimize on both precision and recall, right? At the same time, because you may not just need the precision, but also you need recall. But you can't optimize to both of them at the same time, because when you are trying to optimize for the precision, it is not going to uh, it may not be good at recall, and when you are going to optimize recall, it would not be good at precision, right? In that case, if we say that we want both of the uh, values, you have a weight like equally for each of them for both precision and recall, you can use a single number like F1 score, right? Where F1 score is actually the harmonic mean of precision and recall, right? And this F1 score can be used as the single evaluation metric that you are going to optimize, right, in your project at this phase, right? At the current phase. Once you are good at F1 score, maybe you can define another uh, optimizing objective, and then you can continue, right? So when it comes to developing a machine learning project, it's an iterative process. You can't directly go to the final outcome at a single phase. You have to go for there, here, and there, but you have to move gradually towards the final objectives, or the final outcomes that you have defined in your project, right? And once you are moving to the current objective, right, it would not be moving far away from the final objective, right? So it may be somewhere towards the final objective, right? And finally you would be able to come to the final objective, right? So that is the idea of, it's also similar to the learning process that we do in machine learning, but when it comes to developing the project also, you have to follow the first, if you have several evaluation matrices, you have to come up with a single number at a time, so that your whole team can focus on the single number and optimize into this particular number. For example, the F1 score, right? Instead of focusing on precision and recall, you can focus on the F1 score, so that you can uh, focus your attention towards the reduction of F1 score. But for some optimizers, having a single number like F1 score might not be intuitive, right? For example, take this example, right? Uh, Say like you have a mm, machine learning model, right, where you are going to uh, capture the images from your CCTV camera, right? And you are going to find whether a cat is there, right? Right? Whether a cat is coming to your garden or not, right? So it should be there are several objectives for your machine learning model. One is the accuracy, right? So once you see something, it should be identifying whether this is a cat or not a cat, right? And the other objective is the running time should be minimized. For example, when you detect something, it would not take more than 2 seconds to identify whether it is a cat or not, right? Because once you, if you takes a minute or something, maybe the cat has already moved. Once the model is uh, sending a message to the owner of the garden so that he can capture the cat or something, right? Before the cat is moving away, you have to notify the owner of the garden that the cat is there, right? So the running time should be minimized, right? Uh, so maybe you can think of having a single optimizing number, something like this: zero point 0.5 times accuracy minus zero point 0.5 times of running time, right? So this is the number that you have to increase, right? Maybe you can have this kind of single parameter uh, to optimize, but that doesn't make sense, right? Because what we are really interested about is the accuracy of the model, right? If your model is 80% accurate, we want to make it 90% accurate. If it is 90% accurate, we want to make it 95%. If it is 95%, we want it 98% accurate, right? For the running time, it should be minimum, right? So we are not that much interested about reducing the running time to the nanosecond level, right? So you don't need the image classifier to run within nanoseconds or something. But if it can be run within 2 seconds or 5 seconds, then it is sufficient, right? So the running time is not, we want to reduce it, but we don't want to optimize it too much on this one, right? So we want some uh, upper bound for this running time, and what we want is mainly to optimize on the accuracy, right? So this number is not, although this sounds uh, mathematically correct, but it is not, it doesn't make sense, right? So say like if the running time can be done below 100 milliseconds, then that is almost sufficient, right? So maybe we can, our requirement is to keep the running time lesser than 100 milliseconds. All the other attempts should be given to reduce the accuracy, right? Not to reduce the running time to nanosecond level, right? That is not important at all, right? So in this kind of scenario, it's not good to think about a single optimizing variable, uh, right? Uh, in here, what you can do is you can take accuracy and can be taken as an optimizing matrix, because that is what we are going to optimize. And you can take the running time as the satisfying matrix. Satisfying means uh, if it is satisfying this limit of 100 millisecond, that is what we want, right? We have a certain threshold of satisfaction. If the threshold of satisfaction is made, that is sufficient, right? our, our main objective is of the optimization is on the accuracy, right? Accuracy is where we are going to optimize in each iteration, while keeping the satisfying matrices satisfied, right? You are trying to keep the satisfying matrices satisfied, that means running time below 100 milliseconds and so on, while optimizing the optimizing matrix. Actually, there can be more than one optimizing, so there can be more than one satisfying matrix, like the running time or something else, right? So the availability of the model, sometimes the power or the power consumption of the model, something like that, right? So it should be running within 10 watts of power or something like that. Maybe you can't use a very large visual model. So that is obvious, right? So that is also maybe you need the power to be less than 100, 5 watts or something, right? As a satisfying metric for your model. But you are not going to optimize for the power, right? So you don't need it to be run within 100 milliwatts or something, right? So you just want it as a satisfying metric. What you are trying to optimize is only on the accuracy of the model, right? So when you have several requirements to be satisfied, first you have to find what is the most important thing that you are going to optimize, and then you have to identify the other uh, satisfying matrices and uh, find their thresholds, right? So you can take another optimizing satisfying metric like this, right? For example, you make a trigger word or wake word detection system. uh, in the real world, you can take Alexa or Amazon Alexa or Google Siri or something like that, right? Or OK Google or something like that as a wake word or trigger word detection system. Suppose you are going to make something like that, right? So when you say something like Alexa or OK Google as the trigger word, the system should wake and start to listen to your input, and it would start to execute your commands, right? So when it comes to this kind of trigger word detection system, right, the accuracy should be maximized. Accuracy should be maximized. Therefore, it should be taken as the optimizing metric. And while that is being the optimizing metric, there can be situations where the wake word or trigger word can be detected in false positive way, right? These false positive detection of trigger words should be below a certain level, right? Certain value, right? Like once a 24 hours, right? So that requirement can be taken as a satisfying metric, right? So false positive uh, reduction can be taken as a satisfying metric, right? And when there are multiple matrices to be optimized, you can take a single metric, right? Taken as the optimizing metric can have the other threshold, other variables as satisfied matrices, and have their minimum and maximum thresholds, right? So that we can focus mainly on the optimizing metric at the moment, right? So once you are optimized for that particular optimizing matrix, maybe you can select some other variables as the optimizing matrix while keeping the other variables, other matrices as satisfying thresholds, satisfying matrices, including the previously optimized optimized matrix, right? Optimizing metric, right? So in this time, maybe you are taking the accuracy as the optimizing metric, but later, once your accuracy is too high, like 90.99 or something, maybe you can go for the reduction of uh, false positive detections, right? From as the optimizing metric, while keeping the uh, accuracy uh, above 99% as the satisfying metric, right? That means, in the summary, what I can say is that time to time, your selection of optimizing metric and the satisfying matrix would be changed, right? You are selecting the most important variable that has to be optimized at the moment as the optimizing metric, and keep the other variables as satisfying matrix, so that they are below or above a certain value until this optimization process is done to a significant level, right? Once it is done, then you can select again for optimizing matrix to which direction which we are going to optimize, and you must make the other variables as satisficing matrix by having maximum or minimum levels, because once you are optimizing a certain matrix, you should not allow the other matrix to move away from the uh, values that you expect, right? So that is why we have to keep them as satisficing metrics once you are optimizing on a certain metric for as the optimizing metric, right? Okay, and now let's move into the training div and validation sets, right? Say you are uh, moving up with the project, right? Or you get the data set, right? You may have a large amount of data, right? You'd have to divide them into uh, several partitions, one for training and basically other one for testing, right? But as you may already know, when you are selecting models or in the model selection requirement, you have to use a different data set or a partition data set for validation, or known as the dev set, right? Validation set or the dev set for selecting the model, right? So you should be uh, testing with that validation set as the testing set, or as the unseen real world data for evaluating the models, right? So once you evaluate these models with validation sets, you get certain numbers, right? So then you select the best model, and in order to evaluate the real world numbers, you have to use the test set only once, right? That is how we are using test set, dev set, and the training set, dev set, and the test sets, right? So you are training with the training set, you are taking the numbers, you are evaluating your model for performance using the dev set or the validation set, and then you find the best model or something, and then you take that model's value, the accuracy, performance with respect to the real world data using the test set. So once you have tested with the test set, you are not going to optimize again using that by changing the hyperparameters of each engineering or anything like that, because in that case your selected model would be getting optimized to the test set, because the test set uh, the purpose of the test set is to represent the unseen data in the real world, right? So if you are using the test set for optimizing for a model, that means you are trying to make a model that is optimized with the test set. Yes, the model would be working good for the test set, but it would not be working well for the real world data. So when you try it in the production environment or the real world, it would not be giving the accuracy numbers or the performance numbers that you are observing with the test set, right? So always you should do the uh, you should evaluate the models with the validation set or the dev set, right? The same name, right? So validation is set is also the dev set and so on, because the same name is there, right? We call the validation set as dev set and dev set as the validation set and so on. So you should use this dev set for evaluating the model. That means how accurate it is and so on. And test set only for the publishing the numbers from your selected model, right? That should not be used for selecting the models or tuning the models, changing the uh, data engineering decision making or anything like that, right? That is the idea of training, dev, and test set. So when you are taking the when you are making a training set, right? This training set can contain any amount of synthesized data or augmented data, right? So in the real world problems, you won't have enough data, right? You will not have sufficiently high quality data for your model to be trained. So you may need to synthesize more data using uh, image generator or text generator, something like that, or you can use some algorithms to synthesize data. And you may be able to augment data. Data augmentation means you can, for example, if you have a set of images, you can augment that data. That means change this data and create new data points. Right. For example, if you have an image, you can flip the image right to left, right, and you can make another image, right. So in the first image, it would be left and right. So in the other image, right would go to the left and left would become the right of the image, right. So that is the mirror uh, image of the first image, right. This would happen, right, when you are uh, generating the new images. So this is known as this is a data augmentation technique, right. Or you can crop the image, something like that, right. You can zoom the image a little bit so that it would be the newly cropped image would be somewhat different from the original image, right. You can change the orientation a little bit, something like this, right. You change the angle of the image from the vertical alignment, right. So you could get another image, right. You can change the colors of the image, like you can add a filter of mist or rain or something like that, right. Similarly, you can change the background when it comes to the voice, right. So you can record certain person's voice in a studio environment, and then you can add different background noises like raining noise, forest uh, environment noise, or something like that as the background, and then you can create more data points. That is known as data augmentation, right. You can add more data augmenting using the augmentation techniques. So these techniques are required because in deep learning models you need a lot of data to be trained, right. Because with less amount of data points, the models will get overfitted and they will not work well, right. So when you are using these kind of augmented data or artificially synthesized data, you should be adding this mainly to the training set. But when you are uh, using the validation and test set, you should be trying to using higher quality data, right. And this dev set and test set should be using for, or the dev set or the validation set should be used for training the models that are generated by the training process, right. It can be used for feature engineering and hyperparameter tuning, right. And test set should only be used, the highest quality data should be used for the test set, because the final evaluation for the model is given by the test set, right. So because of that, your test set should be in the highest quality, right. Otherwise you would not get real numbers. Real means the realistic numbers, right. So if suppose you want to use the test set as well, because for training, because you don't have enough data, in that case you can use a technique like cross validation, so that you can use some of the data for test and the other one for training, some for, and partition your data set and use this data set much more efficiently using a technique known as cross validation. In the extreme case, you can use one lever of cross validation, so that you can use the maximum amount of your test set. or test set or training set, right? Or the validation set. But the idea is that you should be using the highest quality data for testing set. You should not be use the synthesized data or the generate augmented data for test set, because they are not the real data, right, related to our problem. And also, when you are dividing the data into dev sets and test set, you must make sure that you shuffle your data before you divide these partitions into training, tests, and training, validation, and test, right? For example, take the example like this, right? You take the Z scores of the students, right? And then you have the districts, right? So if your data set is so that they are uh, ordered in the descendant manner with the Z score, right? Like 4 point, sorry, not 4 point, like it's like 2.28 here for Colombo or something like that, right? So these are related to, suppose these are related to university and something like that. 2.2 for goal and something like that. And finally, you would find like 1.8 for Kilinochi or Mulatiu, something like that, right? Because this data set is ordered so that it is ordered in a descendant manner with Z score, right? If you have taken, if you have divided this data set to training set and test set without shuffling, what happens is you will be taking the different distribution of data for the test set than the training set, right? Because in the training set you have taken the highest Z score districts, and for the testing set you have taken the lesser Z score districts. So these distributions are different, right? So first you have to shuffle all this data together. Shuffle means mix them together, and then you have to take 20% for testing and 80% for training or something like that, right? And there's another thing when it comes to deep learning, right? Compare, this is something different from the traditional machine learning, where we are using smaller data sets for statistical machine learning and so on. When it comes to deep learning, generally you are using very large data sets, right? Maybe like 100 million data points. In that kind of scenario, uh, we are not going to use a ratio like 80-20 or 70-30 like that for training and test partitions, right? We are using 98% to 2%, 99% to 1% kind of proportions for training and testing. Why is that? So these deep learning algorithms are very hungry at data. That means when it comes to deep learning algorithms, you can make them much more accurate, more and more, by increasing the number of neurons, layers, and so on, while increasing the amount of data that is used for training, right? So once you have larger and larger data sets, that means high quality data, right? If you add more noisy data, then the accuracy of the model would get reduced. But if you have high quality data, to with higher quantity, you can get a higher performance model by making your model larger, right? Making your neural network larger, you can have a highly accurate model. In this kind of scenarios, it's better to use most of your data for training. So why then we are using lesser amount of proportion for testing? Because if the uh, variance of the data in the testing set is not that high, that means if the total data set has a lot of data, making 1% or 2% data for testing or validation is not a bad decision, right? For example, you can use, if you are using training dev and test sets, you can use 98% of data for training and 1% of data for validation and 1% data for testing, right? So 98% of data is used for training, and using lesser amount proportion of data for development and testing is not a big problem, because when it comes to 100 million data points, having 1% of 100 million is 1 million data points, right? Taking 1 million data points for validation is more than enough, right? For the test also, the same applies, right? So when you are using 100 million data points for testing, that is more than enough for testing, right? For the size of the data set, right? So using 1 million data points for testing is more than enough for having a very highly accurate number. Because of that, we can use this kind of proportions when it comes to larger deep learning models compared to traditional statistical machine learning models where you are using several hundreds or something like that range of data points. Say, and there's another thing that you have to do when you are you are weighting your data sets, right? Suppose you are using a classifier, right? For classifying for your kids, right? For image classifier, where you can use you can classify your images to toys and non-toys for the purpose of kids, right? You randomly download some toy images from Google or somewhere, right? And you are trying to uh, classify all the all the toys in that image set for the purpose of children, right? Suppose so when you are using these kind of algorithms, there are times when you face some unthought or previously unplanned uh, issues happen, right? For example, suppose now you are using this algorithm for classifying toys, but your machine learning algorithm is classifying sex toys also as toys, right, in this algorithm, but that is not uh, this is because this is used for the purpose of kids, right? So you should not be showing sex toys for the as toys for children, right? So in that case, when you are using this kind of algorithm, you must be having a very high penalty if the model is classifying sex toys as toys when it comes to the classification, right? So when you are using this cross entropy loss, right? So this is the cross entropy loss that we are using in general, right? So this is actually not the loss, actually this is the cost, right? So when you are using this cost function, instead of you can update this cost function so that you can add a weight value, right, to the for the cost equation, so that if the if the image is an ordinary toy, the weight can be for the cost can be taken as 1, right? If it is a sex toy, right? So very which is very unappropriate for the purpose, right? You must add the weight like 100, which is many times higher than 1, right? So you had a very high weight for the inappropriate situation, for the inappropriate cases when it comes to weighting this image in the cost function, right? So when you are, instead of just having ones or zeros, right? So whether this predicted value is equal to the actual value, you can take either 1 or 0 using this loss function. And if this one is really a toy, it would be multiplied by only 1, right? So otherwise, if it is not a toy, it is fine, it is 0. Uh, so if it is a toy, it should be if they are not equals, it would be 1, right? If it is a sex toy, and if in that case you should at a weight of 100, so that it would be having a very high loss, right? So when you are adding these values by to compute the uh, cost function, also you have to use these weights, add these weights, right, when you're calculating the cost, so that in your algorithm you will not be having uh, almost you will have almost no sex toys in the image set that you are using for your children, because you are adding a very high penalty to the highly inappropriate images, right, for the purpose. So these kind of uh, actions can be taken when you find that your algorithm is doing something highly inappropriate or doing something totally against your policies of your project, right? So you can add these kind of weights for uh, these kind of in once you identify these kind of things happen which you have not planned in the earlier phases of your machine learning project. Okay, and also when it comes to accuracy level benchmarks, right? We have to keep this in mind, right? So when you are uh, evaluating your project, right, you have to evaluate them against benchmarks, right? So we have to have some numbers in your model so that you can uh, take the decisions whether you should improve, for example, whether this has the higher bias problem or whether this has the higher problem of higher variance. If this has the higher bias, you can maybe you can increase the size of the neural network and reduce the bias. If this is the problem of variance, maybe you can add the regularization and reduce the variance, right? But for that you have to have some numbers, right? So when it comes to the machine learning problem, the highest theoretically possible accuracy level, right, is known as the base optimal error, right? So base optimal error is the theoretically theoretically least amount of error that is possible with your algorithm, right? So why this error is there? So this is due to the nature, right? So no algorithm can uh, reduce the error level beyond this base optimal error. That is the idea of using this base optimal error. So whatever the algorithm that you are using, due to the nature of the data or due to the nature of the other things, this base optimal error cannot be. This is the minimum level of error that you can achieve with your algorithms, right? Any of the whatever the way you use the algorithms with your data set, that is only what you can do. So actually, we don't know actually what is the number for that error. So we assume that there's a value known as base optimal error, right? So okay. So when you are uh, using the humans uh, with to interact with these models, right? And when you are using humans to classify, for example, if it's a classification problem, if you are using humans to classify the models, classify the data, for example, the human level performance is known as the performance that is given, that is the accuracy level that can be achieved by a an ordinary human, right? Because humans are very good at identifying images and sounds. So when it comes to image and sound related problems, we can take sometimes we can approximate human level performance or the human error as the base optimal error, right? Because we don't know actually what is the base optimal error, but if you can use humans to classify these images, the human error may be uh, we can approximate it as the base optimal error, right? But in general, because humans are also a form of models, uh, this human level error is actually somewhat higher than the base optimal error, because base optimal error is the truly uh, possible, the least amount of error that is possible. But when it comes to human, there's a small human error that is added, right? So this human level performance is generally much higher than the base optimal error. So no human, no anything can go beyond the base optimal error. That is the theory, right? So, but in practice, we are sometimes we are using the human level performance as the base optimal error when you want to have the benchmarks, right? However, with modern deep learning models, uh, because we have a lot of data and so on, and there are some certain uh, s- like generative adversarial networks and those kind of things that where the models are competing with each other and so on, we were able to achieve much higher accuracy than human level accuracy, right? Or human level performance could be surpassed with by the deep neural networks. So sometimes you may have much higher level accuracy, or you can have base optimal, you can go much more closer to the base optimal error than the human level error using the models themselves, right? So, so suppose that initially we have labeled the data and we have found the human level error, but later you have developed a model with much higher accuracy, and now you have found that your model is far better than the base optimal error, right? That is not possible, because base optimal error is the theoretically lowest error. But what really happened was that you have approximated the human level error as the base optimal error, but now your model is working far better than the human level error. So now the model has moved much more to a much more lower level of error, which is closer to the base optimal error. Actually, we don't know what is the base optimal error at all, because there's no way, right? So no one is telling you, but you can, maybe you can take some approximate values to the base optimal error, thinking that it is there, right? Okay. And when you are developing several models, right? So in your machine learning project, you may be developing several models so that you can go to your final objective, right? So in each of the model, you may be evaluating with humans, maybe for approximating the base optimal error, right? And also then you will get training set error and dev set error, right? You are not using the test set error, because you that is taken finally. So in here, in this case, we are not giving the test set error, but you are using training set error, which is the error that you get when you are applying the model on top of training set. And uh, when you are using the dev set for evaluating the model, you get the dev set error, right? Human error is when the uh, how much your data is can be classified with the error by a human himself, right? Not using a model. Actually, if your model can be like a model can be approximate to the this human level error can be approximated to the base optimal error, right? So in that case, you can have a certain level of error, right? So in the first model, say that so in any of the cases, right? Uh, you can find with the human, you can find this model has 1% of error for the first model, right? So we assume that is the base optimal error because there's no other way to find the base optimal error, right? For the model 2, the human with the human, you find that the error which is approximate to the base optimal error is 7.5, right? So the training error is 8.4 model 1 and 8.4 model 8% for model 1 and 8% for model 2. For the dev set, it's 10% for the model 1 and 10% for the model 2, right? Suppose in all these cases, this is how you find the bias and variance, right? So you can use the base optimal error and the training error, and then you can find the bias, right? Because this bias can be reduced, right, with the much higher accuracy, with the better machine learning model. That this bias is known as avoidable bias, right? This bias can be avoided. That is why it is known as avoidable bias, which is the uh, error difference between the optimal base optimal error and the training error, right? When you can take the training error as same as the Bayesian error, that means there's no bias, right? That you take the bias to zero doesn't mean, right? Or you take the avoidable bias to zero doesn't mean your bias, your error is zero, right? Still you will have the base optimal error, right? So it is 1%, in this case 1.5. But what you mean by reducing the bias is actually the reducing the avoidable bias. Avoidable bias is where the what is the difference between the optimal error, base optimal error, and the training set error, right? That is the only error that you can actually avoid it. You can't avoid the base optimal error, right? So in the first case, uh, the difference between the base optimal error and the training set error is 7%, right? In this case, it is 0.5% because it is 7.5 to 8%, right? So the difference between the training set error and the dev set error is the variance, right? Because the training set error, uh, the dev set error is higher than the training set error because the training set is much more uh, fitted to the model, right? But the dev set have not been seen by the model. So the difference between the training set and dev set, so in this case 8% and 10%, the difference is 2%. This is the variance in the model 1, right? For the model 2, the variance is 10% minus 8%, which is 2%, right? For the both models, the variance is the same, but for the model 1, the avoidable bias is much higher, which is 7%, and for the model 2, it is 0.5%. So when it comes to the model 1, what should you do? You should reduce the higher error first, right? So what is the highest error? 7% or 2%? It is 7%, right? So the 7% is the error that has to be reduced first. That means avoidable bias should be first reduced in the model 1, right? But when it comes to the model 2, what is the error that you have to be, which is higher, right? The avoidable bias is 0.5%. The variance is 2%. So in this case, variance is higher than the avoidable bias. So the model 2, you have to reduce the variance first, right? So in the model 1, if you have developed a model, if you are using the model 1, you have to, the next step is that you have to take the action for reducing the avoidable bias, which may be related to increasing the sizes of the parameters, reducing the so increasing the training time if you are using early stopping. If you are using much higher regularization, you can reduce the regularization, or you can increase the data set if it is possible, right? But for this model 2, first you have to reduce the variance because the avoidable bias is little, right? Much more smaller. So in order to reduce the variance, what you have to do is you can increase the regularization, you can increase the data set, and so on. So depending on the model and depending on the errors that you get for the Bayes optimal error or its approximation, which is the human error, and the training set error and the Dev set error, you can calculate the this avoidable bias term and the variance terms, and then you can take decisions into which direction that you should move, whether you should reduce the bias or the variance. That is how you make decisions in your project uh, in the current state, from the current state, right? And when you are making decisions, optimization decisions based on errors, right? Uh, First, the base optimum performance has to be decided, right? So if you don't have any good benchmark for a good value for the base optimum error, you can use human level performance, right? And then you have to find training and dev set uh, errors, right? Training set errors and dev set errors. And if this avoidable bias is greater than variance, uh, and you have to take the measures to reduce the avoidable bias. And if the avoidable bias is lesser than variance, you have to take measures to reduce the variance, right? If the human level performance or similar measure is used as the base performance, right? While training error or testing error is lesser than the base performance, so then it would be become a problem, right? To make decisions. So that also you have to keep in mind, right? That means if the human performance or similar measures used for base performance because you don't have any other base error performance measure, and then you find that the training set or the test set error is much lesser than the not much somewhat lesser than the uh, human level error, right? So then we it's like you have got a model that is uh, much more accurate than the base optimum error. That is not possible. What really has happened was this model has exceeded the human level performance, right? That is what has happened. So in that case, you can't use these numbers for making decisions. So then in that case, you would have to go for different forms of techniques, not the one that we identify here. Right? So so let's so we are not going to discuss what to do next, right? So in here, just look, we see what are the problems where the AI is passing the humans, right? When it comes to solving problems. So the first thing is that you may think that only current deep learning models are surpassing the human level performance, but that's not the case, right? Even before the advancement of deep learning in classical machine learning also, when we are using structured data sets for statistical and machine learning models, these models are even better than human level performance. Say like you have a set of features that you have collected for online advertising decision making, right? To which person you have to advertise. So maybe you have used a classical model like gradient boost or something, right? Or random forest. These models may be better than giving them these numbers to a human being, because looking at these numbers, like which browser the this particular website was accessed, in which geolocation these people have come with, and with all these data features, the human can't actually comprehend all these values, right? So the computers were still better than human when it comes to making these kind of decisions, or product recommendations, like in Alibaba or eBay, right? So still the AI was standing above, right? And when it comes to logistic related predictions, like tra- time to transport, or predicting the time of arrival in Google Maps or something like that, still the AI was far better than human when it comes to predicting numbers. Even in the applications like banking, where the loan approval uh, tasks are automated with AI, AI was far better in accuracy than humans, because AI can numerically analyze a lot of data, and systematically they can uh, identify identify the tendencies, right, better than a human, because a human can't uh, keep a lot of data and process a lot of data and come up with highly numerical accuracies, right? But humans were better at natural world related objects, like object identification, object classification, natural language processing, and video processing, and so. But with the development of uh, neural networks, right, deep neural networks, now they are better at speech recognition, image recognition, and medical diagnostics related stuff like ECG reading, and image computer vision problems like detecting skin cancers, or radiography related image classifications like mammography classifications for diagnosing cancers. Today's AI is based on deep neural networks are far better in performance than human beings. So that's all for the today's lesson. And if you have any questions, you can ask.